Okay, so first let me explain what object I'm talking about. So let's suppose we are given some space which can be three-dimensional sphere, three-dimensional Euclidean space, or three-dimensional hyperbolic space. And we consider a geodesic tetrahedron in one of those spaces. So such a tetrahedron has 12 interesting parameters for me. So L12 up to L34 are lengths of edges. And the indices correspond to the edge. And alpha 12 up to alpha 34 are dihedral angles. So angles between planes. And so basically the main question is how these numbers are related. So of course, they are related because the space of parameters for spherical or hyperbolic tetrahedra has dimension 6. And so if there are 12 parameters, we expect that they generate some 6-dimensional subvariety there. And it is quite clear that relations between lengths of edges and angles will be transcendental, involving sines, cosines, and so on. But it is quite easy to convince yourself that relations between their exponents. So I will assume I'm working in hyperbolic space just for completeness. It's not too important. So relations between exponents of angles and exponents of lengths of edges are algebraic. And the question is to find them. So another way to think about it is that we can think of a space C cross power 6 times C cross power 6, where for every tetrahedra, we get a point with coordinates exponent of dihedral angle and exponent of length of edge. And inside, all tetrahedra generate points of some real 6-dimensional variety. And if we take algebraic closure, the risky closure, then we get a 6-dimensional variety inside this 12-dimensional torus. And let me call it T. So this is a closure of the locus of hyperbolic tetrahedra exponents of angles and edges. And the question is basically find T. And by that, I mean, of course, find equations for T and understand them and so on. So to make it a little bit more interesting, let me immediately say that T has an interesting property. It is Lagrangian with respect to a natural symplectic structure here. So if I denote exponents of angles by xij coordinates and lengths by yij coordinates, then T, so this is a little theorem, which is called Schlafly relations or identities, that T is Lagrangian with respect to most natural sum dxij over xij wedge dyij over yij symplectic structure. And moreover, its generating function is actually hyperbolic volume. So this comes from the relation due to Schlafly that differential of the volume of a family of tetrahedra equals to sum Lij d alpha ij. So this is just known from 19th century. But explicitly proving that this is the case from any kind of algebraic relations is non-trivial thing. And one can understand this problem also as a problem of trying to compute the volume of tetrahedra explicitly. And already here, probably one can notice some relation with 6J symbols. And basically, I'm not going to get into all details. The idea is that 6J symbol for quantum group UQSL2 or just usual SL2 satisfies certain difference relations. And if one looks at their symbol, one gets algebraic relations. And these are actually equations for T. This is the relation. And from these heuristics, one can probably come up with ideas that there is this asymptotic relation between logarithm of 6J symbol and the hyperbolic volume. But I'm not going to talk about that much. I don't have anything new to say there. So what I will concentrate on is understanding this T and basically giving a completely different way to think about it using algebraic geometry. So let me try to convince you first that there is a reason for introducing some new ideas here. So there are some facts about T, or basically about trigonometry, which are quite surprising. So let me first say a few things about them. So the first idea is that there are some interesting trigonometric relations, which let me start with another one. First, let me talk for a few minutes about Regge symmetry. So Regge symmetry. So this is a fact about trigonometry of tetrahedra, which I will say in a second, which is also known for 6J symbol, and it was noticed by physicist Tullio Regge back in probably 50s. So here is a statement. So let's suppose we are given a tetrahedron in one of the spaces, say hyperbolic, and this is tetrahedron T, and it has lengths of edges Lij and dihedral angles alpha ij. And then let's imagine that I construct another tetrahedron T prime out of it by the following very strange and simple rule. So the angles, lengths of edges of tetrahedron T prime are related with those of tetrahedron T by a very simple reflection formula. So let me just write down explicitly. The first lengths 1, 2 and lengths 3, 4 do not change at all. And for the remaining lengths, there is a relation sorry, 1 second, 2, 3 minus L1, 3 over 2. So there is a reflection. So if I denote by P the sum of all other lengths of edges, then for the remaining, I just do this reflection. So let's imagine I do that. And of course, such tetrahedra might not exist, or might not, because of, say, failure of triangle inequality or something like that. But let's imagine it actually exists. Sorry, there is a question? Yeah, okay. So suppose T prime exists. And then the following is true. So firstly, volume of T is the same as volume of T prime. And secondly, one can compute angles of T prime. And for angles, the same formulas hold. So I will not write all of them down, but just literally the same formulas with substitution of angles instead of lengths of edges. The fact which was noticed by Regge was the fact about volume of Euclidean tetrahedra in this fact. And then slowly these things were conjectured, and now there exist two proofs which appeared more or less simultaneously. So the proof of the theorem, one follows from what I will explain today, and the other is known from a recent work of Akapian Zmestiev called The Name Involved Regge Symmetry. So this fact is miraculous, and if you think about it, it tells us that this locus T has a lot of symmetries. So basically, there is an action of a Weyl group on it, which I will explain a little bit later, and all these equations are invariant with respect to this action. And in particular, so it is also known that similar symmetries exist for 6J symbols and are, I guess, considered a little bit mysterious as well. So my main goal will be to explain that. Basically, I will show that this locus T from previous, let me use T curve T for that from previous slide actually is invariant under a group, the Weil group of root system of type D6. So basically different parts of the section correspond to S4, just relabeling the vertices of tetrahedra. Then there is this Regis symmetry, and there is also another kind of symmetry which takes for some ij substitutes length of edge with minus length of edge and dihedral angle with minus dihedral angle. So this is natural symmetry of trigonometric formulas. They are true. If you take any trigonometric formula and apply any element of this Weil group, you will get a correct statement. So, and again, my main goal is to explain why this happens, because it looks a little bit miraculous and it's actually very hard to prove directly. And there is another fact which is also very simple to formulate and is very hard to prove, which is new. So let me mention that now. So theorem. So let's suppose that we are given a tetrahedra like before, and let's introduce new parameters. So P1, P2, P3, P4 are just perimeters of faces. So for instance, P1 will be L23 plus L24 plus L34, and so on. Just usual perimeters. And omega 1 up to omega 4 will be what's called solid angles. And they are basically angles. And they're basically just sum of dihedral angles minus pi, because it's actually angle of a part of a unit, one radius 1 sphere with a vertex in this point. And so by Gauss-Bonnet, one can write it down using dihedral angles. This is an example. So let's look at these parameters. And then the following statement holds. So if one takes cross ratio of exponents of dihedral angles, solid angles, then this cross ratio equals to cross ratio of exponents of perimeters. And if you want to do Euclidean case, the same formula holds, except on the other side, you just take perimeters without exponent. So this is for H3, and the second formula is for R3. So, so this is a very simple statement, of course, and this is remarkably hard to prove. So now there exists, there exists the original proof, which I will explain today, with algebraic geometry, and there is an interpretation with mixed plot structures, such stuff. Then there is a proof by Greg Egan, who actually just opened brackets, but he remarkably found the transformation which exchanges these tuples of points. Sorry, by the way, so this is just cross ratio. A, B, C, D is just A minus B, C minus D, A minus D, B minus C. And also recently, actually a few months ago, Fedya Petrov obtained a proof using completely elementary methods, and it's a matter of law, but it is pretty long and pretty complicated, involving some geometric constructions and some trigonometry. So it's pretty hard. Anyways, so
question.
Yeah, sure.
Isn't it possible to prove it using computer algebra just by asking?
Yes, certainly.
Of variables and so on?
Yes, absolutely. One can prove all of the statements using pretty simple. But they are hard again. So these computations will require care, and one can do it. But of course, our goal is to understand them, to explain them. And the main idea is that I can come up with a proof. So I will explain today the proof which does not involve any computations at all. Mm-hmm. So this is the goal, and explains where it comes from. And also, if you combine these two statements, one can actually use the Weil group and use it to generate other equations. And one gets 22,000 equations which are related in a non-trivial way. Most of them are not equivalent to each other. And they all describe this. So one can think of these equations as a very nice equations describing this locus of tetrahedra T inside of the product of two tori.
Where does 22,000 come from?
Because this is the order of Weil group. So order of Weil group is 22,000 something. Yeah, okay. So let me explain the main approach. So the main idea is that there is a relation between tetrahedra and certain algebra geometric objects, namely rational elliptic surfaces. And if we specialize to certain kind of rational elliptic surfaces, it will be a one-to-one correspondence. So basically, there is a vocabulary between trigonometry and algebraic geometry. And this is my main goal, is to explain how does it work and where it comes from, basically. And it comes from theory of mixed Hodge structures. This is the explanation. So, okay, so let me now formulate. So to formulate the main theorem, I need to introduce this algebra geometric definitions. Okay, so I will do it maybe briefly, but please ask questions if there are any. So, so we work, so my main object will be, so this is part 2, rational elliptic surfaces. And so for this talk, for us, rational elliptic surface will be, one can just think of blow up of P2 at 9 points, which are intersections section of 2 cubic curves. So the picture is like that. And then we blow up 9 points of intersection of 2 elliptic curves. So so let's suppose X is a rational elliptic surface. So the main feature of rational elliptic surfaces, so they are complex projective 2-dimensional surfaces. Smooth, projective, yeah, 2-dimensional. So the main feature of this object is that there is a map from X to P1, which is given by anticanonical pencil. And what this map actually does, so one can look at, so P1 is actually just projectivization of vector space of pencil of all elliptic curves containing these points P1 up to P9. And these are points up to P9. And the map just takes a point on the plane and constructs a unique elliptic curve passing through this point and 9 points which we blow up. So this is the map, and fibers are so the generic fiber is an elliptic curve, and then there are some degenerations. So fibers are, so most fibers are elliptic. But they can degenerate, and there is Cadiral classification of these degenerations. And so typical fiber looks like elliptic curve, but also there are different degenerations. There are nodal degenerations, then there are reducible degenerations, and cuspidal, and so on. So there is a huge list, which is completely known. So for me, the most important type will be the type where there are 2 rational components intersecting in 2 points. So it's called I2 fiber. So the nodal one is called I1 fiber. So a generic rational elliptic surface has 12 I1 fibers in this anticanonical map. And one can easily see that the dimension of moduli spaces of all rational elliptic surfaces has dimension 8. And if I want to make a correspondence between them and tetrahedra, I want to reduce dimension. So let me give a definition for this talk. So so a rational elliptic surface of type D6 is a rational elliptic surface with a pair of I2 fibers. Let me call them F1 and F2. And I consider it a part of the data. So basically, one can think of this surface. It has a map to P1. Most fibers are elliptic. There are 2 fibers which have this type I2. And actually, there is 8 more nodal fibers, but they can degenerate arbitrarily, I don't mind that. But most importantly, two fibers I2 of I2 type are fixed, and they are not degenerated in any way. So moduli space of such curves has dimension 6. And just to give an example, one can, for instance, just take both elliptic curves being reducible. So for instance, a union of an ellipse and a line intersected with another union of an ellipse and a line, and blow up 9 points of intersection. And this will be an example. So, and all examples are obtained via this construction, so it's pretty general case. Okay, perfect. So now why it's called a rational elliptic surface of type D6, and what has it to do with D6? So the reason is very simple. So one can look at, Picard of X, and it is a lattice of rank 10. And inside there is a vector F, which is this anticanonical class. And also this is the class of the fiber. So that's why it squares to 0. And if one looks at orthogonal complement of F factor over F, this is lattice of type E8. So this has intersection pairing, so it's lattice of type E8. So it has many roots, of course, infinitely many roots. Sorry, 240 roots. And so just to give an idea what actually roots are, so roots are all differences S1 minus S2, where S1 and S2 are non-intersecting sections. Or classes of reducible components of fibers. So basically roots come from these two places, and it is indeed very easy to see that for instance, if one looks at these two fibers of type I2, each of them has two components, and each component is a curve with square minus 2, which produces a root vector inside this Picard lattice. Okay, so finally, let me introduce this notation. So let's suppose, again, I'm given this surface, and I have these two fibers. And so let EA and EL be, so these are classes of a component. So EA, for instance, will be class of the first component of the fiber, this one, and EL will be a class of the first component of the second fiber, for instance. So then one can easily see that actually, so EA is a root, and EL is a root, and both of them are orthogonal to the canonical class, to F. And orthogonal to each other because just these components don't intersect. And so eventually one can look at lattice EA, EL orthogonal factored over F. And this has clearly rank 6. And this is lattice of type D6. So in particular, while group acts on it, and this will be important later on. So let me denote this lattice like Z of D6. Okay, so so far nothing happens, but then let's think about this moduli space of these rational surfaces with these properties. So it has dimension 6, and it will be interesting to introduce some parameters there. So how to introduce parameters? So the idea is very simple. So it's called period map or Leyenha period map sometimes. So let's take, so if one looks at this lattice, Z of D6, oops, sorry, Z of D6, there are two canonical maps. So one is a map to peak knot of the first fiber, and another is a map to peak knot of the second fiber. So what does this map look like? So abstractly speaking, it's just restriction map. So this lattice, after all, elements here are represented by sheaves, invertible sheaves on the surface, and one can just restrict them to the corresponding curves. And in practice, what it looks like if you take, for instance, a root here, which looks like a difference of two sections, like this, then if it happens that both sections intersect the same components of the fiber, then the image of this S1 minus S2, oops, I'm sorry. So let me call this map A and L. And A of S1 minus S2 is just, sorry, L and A. L and A, and L of S1 minus S2 is just a cross ratio of 4 points where I need to look at points x1, x2, x3, x4. So this is just cross ratio of x1, x2, x3, x4 on P1. So so this is just because, so if you look at peak knot of a reducible curve, then it's actually each of these peak knot groups is just multiplicative group of a field, and the correspondence is just by taking cross ratio. So okay, so in this way we get two maps to C cross from 6-dimensional lattice. And of course, one can understand it as getting for every surface. So for every, so X produces for us a point inside a product of two tori. So these are just characters of this lattice, basically. And in this way, we get some subvariety inside the product of two tori, which is of dimension 6. So to do it exactly, one needs to take not just rational elliptic surface, but also mark Picard lattice, identify it with isomorphic lattice, fixed isomorphic lattice, and then it becomes strict. And the claim is that this is exactly this locus of tetrahedra, which I described before. So let me formulate it as a theorem, which is the main result, maybe. So theorem is as follows. For every hyperbolic tetrahedron, T, there exists a rational elliptic surface of type B6, X sub T, and 6 roots in this lattice Z of D6, which I will denote by R12 up to R34, such that on each of this root, for every I and J, the value of Elimap on Rij is exactly the same as exponent of the length of H of a tetrahedron, and dihedral angle of Rij is exactly the same as exponent of the dihedral angle of tetrahedron. So that's the theorem. And of course, I said that there is a one-to-one correspondence, so one should be slightly more careful here. To make it one-to-one, one needs to extend the notion of a tetrahedra to some more general setting, algebra geometric setting, where one can treat uniformly hyperbolic and spherical case, for instance. And then the statement will be that there is a one-to-one correspondence between certainly marked tetrahedra and rational elliptic surfaces also marked, meaning there is a choice of a root basis, for instance, for these lattices. So, so that's the theorem, and let me explain immediately why it has immediate corollaries. So, so Reggie symmetries are obvious from here. And the reason is simply because, so while group of D6 acts on the lattice Z of D6, and since L and A are just linear maps, it will act simultaneously on its images in the same way. And in particular, if you transform exponents of lengths of edges using this Regge symmetry formula, the angles will transform accordingly. So this is just immediate corollary. I mean, to formally prove it, one needs to do something a little bit, just to. But roughly speaking, this is the explanation. So this makes Regge symmetries clear. And there is another relation about exponents of omegas, dihedral, solid angles, and exponents of perimeters. Also is easy to show. So basically, the idea is geometric. So one can look at this rational elliptic surface, and there is a certain map to P1, which is different from the elliptic pencil structure. And this map is what's called a conic bundle. So generic fiber is just P1. And there are lots of such maps. And then there exists a particular map which has the following property. So, so there is a map with, so such map has actually 8 nodal fibers, which are just unions of lines. And for this map, it has a property that there exist there exist 4 fibers. So this line side fibers. And these fibers have a property that the cross ratio of 4 points on the left side is equal to, so this cross ratio of these 4 points is the same as the cross ratio of exponents of lengths of perimeters. And the second cross ratio of 4 points is cross ratio of exponents of the solid angles, and this just follows from work with roots and lattices. There is no computations here. And then this conic bundle just gives an isomorphism between P1 on which the first tuple is defined and P1 on which the second tuple is defined, sending these points to each other. So this proves the second statement about cross ratios. So, so this is maybe a good point for questions. And then I will come to explaining where this construction comes from, basically.
Where does the idea about D6 come from? How do you know that you should work with D6 lattice?
So the fact that D6 plays a role follows immediately if you just look at Regge symmetries and you combine them with usual S4 symmetry of a tetrahedra. And then if you also add this symmetry or exchanging the lengths of edge by minus sign, you will just literally get a Weil group of D6 in its standard presentation. But of course, this is just combinatorics. So then it was a question where this Weil group of D6 came from, algebraic geometry or representation theory or some other ideas. And this is basically where I was able to find it. Okay, so let me now explain maybe the idea behind the construction and also how tetrahedra and surface are related, because I have not said that actually.
I'm sorry, may I also ask, can you remind what L and A are once again? Just
so,
recap.
So L and A are, so you mean this big maps?
Yeah.
So these are geometrically defined. So these are called period maps. For XT, and this is because they resemble basically period maps for K3 surfaces. And what they do, so again, if one takes this root Rij, which is represented by a difference of 2 sections. So suppose Rij is a difference of 2 sections, S1, S2, or of the elliptic fibration. Then if one takes these 2 sections and restricts them as divisors on the components of the fiber, one takes difference of points on one fiber and difference of points on another fiber. And inside the group peak knot of the fiber, which is just C cross, every difference of points gives a number, which is a cross ratio. And similarly on the other side.
Thank you.
Sure. Okay, so for that, let me explain a little bit the algebra geometric picture behind hyperbolic geometry. So this is something which is familiar. So Klein's model. So let's consider usual H3, and this is just interior of the ball. And so the boundary of H3 is just the sphere. And let's embed, yeah, and in Klein's model, geodesics are just segments. So segments of straight lines connecting points of the boundary are geodesics, and planes are plane geodesics. And also lengths between 2 points. So if one has 2 points A and B, then one looks at XY, where XY are intersection of line AB with the boundary. And the length between distance between A and B equals to logarithm of cross ratio AX BY up to some constant. So this is Klein's model, and then one can treat it algebraically. So for that, one can embed R3, where everything goes inside complex numbers, inside projective space, and then this D of H3 is sitting inside this sphere, which sits inside, after projectivization, inside a quadric Q. So this is a smooth quadric. I mean, it is given by equation like this. And of course, every smooth quadric is isomorphic to P1 cross P1. So basically, one has a quadric, one has this P3, and then, so if one has a tetrahedron in hyperbolic geometry, so one can also complexify planes. So planes go to H1 up to H4, which are planes in P3. And so every hyperbolic tetrahedron produces a configuration of P3, smooth quadric, and 4 planes. And basically, this is what I will call projective tetrahedra. This is a natural generalization. The object which has, for which one can define angles, lengths of edges, and so on. So, and here is interesting fact. So actually, if one tries to define, so let me call this T now will be this configuration of quadric and planes. So if one tries to look at this tetrahedra, it is convenient to just draw lines of intersection of planes, and then each line intersects quadric in 2 points. So basically, one has this interesting configuration of 12 points in P3. So these points are just Q intersects HI intersect HJ. And to actually define lengths of edges so that they will be well-defined parameters, one needs to choose ordering of each pair of points. So lengths of edges are defined for marked tetrahedra, and by marked I mean points HI intersect HJ intersect Q are ordered. And this is exactly the reason why in all the stories there is a symmetry which exchanges lengths of edge by sign and the corresponding dihedral angle by sign. So this is exactly where it comes from here. So from here one immediately, so already here it's obvious that if regusymmetry acts in an interesting way on such objects, then one can look at the whole Weilbrook. So this is the answer. Okay, so what one can do with it? So for a tetrahedra, there is a well-defined dual object. So T perp will be dual tetrahedra. And this is just tetrahedron. And this is just when one substitutes each vertex with a plane which is polar to it with respect to the quadric. And then one can define angles of original tetrahedra as lengths of edges of the dual. So in this way, one can actually get this algebra geometric notion, which for which all the statements hold. So what is the relation between t and x? So there are two relations. One of them is cohomological and another is algebraic. So let me start with maybe algebraic one, which unfortunately I cannot explain nicely, probably because I just don't understand it so well. So so actually fact is that xt can be obtained by an explicit blow up, blow down construction. So this is done as follows. So one takes this Q, and then Q should be blown up and then blow down to this xt. So Q is a quadric. This is just P1 cross P1. And one blows up in 12 points, which are exactly this marked points. So Q, oops, I'm sorry. Let me. So so R is a blow up of Q in this points hi intersects hj intersect Q. So so R is blow up of P1 cross P1 in 12 points, and then so R to xt, this is blowing down 4 - 1 curves, but then it's hard to explain which. So this procedure is not canonical, and the fact that one gets isomorphic surfaces for different choices is completely non-trivial. So there is a proof, but the proof is mostly more kind of computation, and I don't understand well algebraic geometry behind this construction. But after all, this is a simple birational geometry operation from quadric to the surface. So, but actually, this relation came from some algebraic geometry of mixed Hodge structures. So let me explain that. So so let's look again at this tetrahedra from the viewpoint of algebraic geometry. So we have this P3, H1 up to H4 are planes containing faces, and Q is a quadric. And then one can look at the following cohomology. H3 of P3 minus Q relative to the union HI minus Q. So and then so this cohomology, so this is cohomology group, and this cohomology group, so this is cohomology, I mean rational, sorry. Say Betti cohomology carries mixed Hodge structure. And so in this particular case, it is of mixed state type, and what it results in the fact that one can actually just see the whole mixed Hodge structure looking at the period map. So there is a comparison between Betti and de Rham cohomology, and by de Rham I mean algebraic de Rham cohomology, and then one can write down the period matrix, and it will have a main term, which is just the volume of tetrahedra, then L12 up to L34, 1, lots of 2 pi i's on the diagonal, 0, 0, and then alpha 12 up to alpha 34, and 2 pi I squared. So that's kind of the structure of this. So this is period matrix for the cohomology. And that's not particularly surprising because, for instance, the volume definitely is an integral over three-dimensional object inside the tetrahedra, over this locus. And one needs to integrate a volume form on the hyperbolic space. And actually, volume form is exactly the generator of H3 of P3 minus Q. It's a three form with poles on the quadric, and such form is unique up to rational constant. So so basically knowing, so let me denote this M of t, sort of motive over tetrahedron, and then knowing M of t is actually the same thing as knowing all these angles, edges, and so on. And one can notice that there is a certain duality here. So if one looks at the dual tetrahedron, then actually this corresponding mixed Hodge structure is just Verdier dual. So on the level of period matrix, it's taking the inverse transpose. And this is well known because it's well known that when you take dual spherical tetrahedra, for instance, angles and edges exchange their role, and there is a simple formula how volume changes. And actually, this is just the statement which I just said. So this there is a dihedral between mixed Hodge structure of tetrahedron and the dual. And the main fact about the surface is actually that H2 of the surface x sub t without F1 relative to F2 is isomorphic to this H3 of P3 without Q relative to the union of HIs without Q. So isomorphic as a mixed Hodge structure. And the fact that period matrices agree is exactly the statement of the theorem I mentioned before that. And in particular, it gives a presentation for volume. So basically, if one takes the surface, then one can look at the integral. So if this is a surface, one can look at there exists a unique form omega form with poles on F1, just because F1 is anti-canonical class. And then there exists some gamma inside H2 of X relative to F2. So some H2. So that integral over gamma of omega equals to the volume. And one can use it to compute volume. And for that, one basically can compute volume integrating over fibers of this map to P1, which I mentioned before. And so computing volume immediately by just integrating by fibers using this projection immediately leads to a formula which is called to Chokim formula. So Chokim formula is a formula obtained for the volume of tetrahedra. It's very explicit but complicated, and it was obtained in, I guess, early 2000s. And there is an explanation of this formula from asymptotics of 6J symbol. So one can look at asymptotics of 6J symbol, apply the standard, the standard quantum volume asymptotical estimation, and come to this formula for volume. And it involves some integral. Oops, I'm sorry. It involves some. So this formula gives a volume of tetrahedron, and it involves some integral between some parameters which can be found by some equation of a complicated rational function of degree 4, which one can look up. So it looks very strange. And so actually this function is just the function which assigns to a point in the image P1 of this conic bundle the cross ratio of 4 pre-images. So this gives a geometric explanation of these results for volume, and this is exactly where the whole story kind of started. So I think that's it. Thank you very much, and I'll be happy to answer any questions.
Okay, thank you very much. Let's thank the speaker. We'll clap somehow. And if there are any questions, please.
I have a question. With you mentioned 6G symbol several times, and there is some kind of natural SL2 component in this story. So I'm sure in this algebraic geometry there is also some role for SL2, because 6G symbols also exist for other algebras.
Right. So so the answer is I don't know, but it is something I want to understand. So the most direct connection which I know between 6J symbol and this story is the only one I actually was able to find, is roughly going as follows. So there is a story about quantum Q-deformed Penlevé equation, and one can look at Q-deformed Penlevé equations, and 6J symbol is one of the solutions, or actually sort of the explicit solution for a certain kind of such Penlever equation. And this Penlever equation is actually can be understood very nicely from algebraic geometry viewpoint, because basically what it results in, one takes a rational surface, but not rational elliptic, but just blow up of generic 9 points on P2. And then, so if you have such a surface, of course, there exists a lot of models how one can construct it by explicitly blowing up P9 in different configurations. And this leads to an action of a while group, infinite while group, basically E81 on P2. And one can understand this Q-deformed Penlever equation as basically this dynamical system. And 6J symbol provides one of the solutions. And exactly for this kind of, so basically this is exactly a way to see these two things appearing on the same picture. But I was not able so far to derive from here a clear explanation of asymptotics, for instance, though it's something I would love to do.
Thank you. Thanks.
Sure.
Any other questions? Anton?
You have this picture where the period matrix, the mixed Hodge structure, the period matrix, you see all the different things appearing as entries. Is it special? Just is it generally maybe for arbitrary for instance, for arbitrary polyhedron in the 3 space?
So it's true for arbitrary polyhedron in any dimensional space. I mean,
in any dimension.
Yeah, one should be slightly careful because if one wants to get exactly the statement like that, one should take tetrahedron. Otherwise, you will just have too many parameters. It starts to be a little bit combinatorially hard. But this is probably observation of Goncharov, and this is this is a key point in his correspondence between Caesar congruence of tetrahedron and mixed motifs. Because one takes a tetrahedron, looks at this mixed Hodge structure. This is an object in the category, conjectural category of mixed state motifs, and then the story goes.
Okay.
So this is general.
Any other questions? Okay, well, let's then thank Danny for a wonderful talk.
Thank you very much.
And next week, we will probably have Sergei Bukov. He should send his title lecture shortly. And yeah, so hope to see you in a week. Okay, thank you very much.
Thank you.
Thank you.
Bye-bye.
Да, спасибо еще раз. А для старшего ранга что-то такое похожее есть, да, там для SLN, например? Ты частично ответил, вот когда про Гончарова сейчас говорил, но это можешь в 2 раза медленнее?
Да, но тут как раз тут проблема немножко вот в чем. Как бы история про тетраэдр-то есть.
Да.
История, которую вот я тут описывал с этой D6 и рациональными алгебраическими поверхностями, ответ я не знаю. Я думаю, что есть, то есть как бы должен быть алгебра-геометрический объект меньшей размерности в 2 раза, грубо говоря,
Да.
который симметрично описывает эту картинку с тетраэдром. Но я не получил пока эту историю. Вот. А вот придумать аналог гипотезы объема, используя какие-нибудь штуки для SLN, я не знаю. И я
ну это отдельно. Гипотеза объема все-таки отдельная история, действительно. Сейчас, а вот эта конструкция как помогает гипотезе объема или нет?
Ну, вот это немножко вопрос. То есть, с одной стороны, я думаю, что ответ должен быть да, но у меня пока не получилось ничего сделать. Но я думаю, что в итоге это сработает по следующей причине, потому что, ну, как бы гипотеза объема, она увязывает очень далеко. То есть, как бы, конечно, там есть эвристика, почему объемы тетраэдров имеют отношение к 6J-символу.
Да.
Но как бы, ну, реально, вот, например, если хочется провести вычисление, там, написав, не знаю, там, идеал соотношений, разностных соотношений для 6J-символа и посмотреть, как он соответствует тригонометрии, то, конечно, можно явно что-то проверить руками, но это дико непонятное утверждение. У него нет красивого доказательства. А вот эта конструкция дает, ну, делать подобные утверждения все красивыми, потому что она описывает тоже пространство модуля тетраэдров совершенно по-другому, так что про него любое соотношение доказать очень просто. Ну, по крайней мере, красивые соотношения.
Ой,
Вот.
сейчас, пардон, я понял, что связь, эту запись не выключу, сейчас я выключу. Сейчас, секунду.